Well, good day, Gators. I wanted to go over solutions and solubility curves a little bit today. So let me go ahead and share the screen. And so solutions and solubility curves. Now, we've already talked about the sun, so a lot of what I'm presenting here is review, but basically in a solution, you have something dissolved in a solvent. And so the solvent might be something like water, and the solute is what is being dissolved in it. So solute is what you're dissolving. So for example, you might have lemonade, and if you put the lemonade mix into the water, the solute would be what is being dissolved, so like the lemonade. The solvent would be the substance that the solute is dissolving in, and generally in chemistry, we will be dealing with a solvent of water. There are other solvents, any liquid could be a solvent, but generally we will be dealing with water as the solvent, and then whatever goes into the water is the solute. Now, there's a few things about dissolving. Generally, a good rule of thumb is like dissolves like. So polar substances will tend to dissolve polar. So a polar solute will dissolve into a polar solvent, and a non-polar solute will dissolve into a non-polar solvent. So something like NaCl is polar, and it will tend to dissolve in water, which is polar. And methane, or CH4, carbon tetrahydride, might dissolve in something as liquid like carbon tetrachloride. And essentially, when you get dissolving, a substance will dissolve if the attraction to the outside solvent is stronger than the attraction within, internally within the solute. So to look at that, we kind of, we'll be looking at, that kind of relates to intermolecular forces. And we said there were three types of intermolecular forces. The first was dispersion forces, which were weak intermolecular attractions. They're most often seen between two covalent compounds, and they're formed as a result of this temporary movement of electrons and thus charge imbalance seen as the electrons move about the compound. A more strong interaction is these dipole-dipole interactions. And there, instead of just temporary movement of electrons, you actually get permanent electron arrangement or irregularity, where you have one part of the molecule will have more electrons than the other. So like water, H2O, there's 4 unpaired electrons, and I'll show some pictures of this in a little bit. There are 4 unpaired electrons with the oxygen, which means the region around the oxygen is negative, and the region around the hydrogen is positive. So you'll get attraction there. And that's actually an example. That attraction is an example of a special case of dipole-dipole interaction called hydrogen bonding, where you get this attraction between, basically in hydrogen bonding, a hydrogen atom and then the very electronegative free electrons of either nitrogen, oxygen, or fluorine. And that's the most strong of the interactions here. So 3 interactions that we deal with in terms of attraction between 2 different molecules or compounds. Dispersion forces tend to be weak. They tend to be seen in covalent compounds like iodine, I2, or something like that. Dipole-dipole is between like NaCl and water or something like that, where it's an interaction between permanent differences in charge within the compounds. And then hydrogen bonding is a special case of dipole-dipole, which again is with hydrogen atom being attracted to the free electrons of nitrogen, oxygen, or fluorine. Now, as a quick review, we've talked about polar and non-polar. In polar substances, you have an uneven charge distribution. So like water has, these dots are representing electrons, and there's 4 free valence electrons here, meaning that around oxygen, there's a negative charge. Hydrogen is just the proton here. The electron helps to form the bond with the oxygen, so you tend to get a positive region here. So there's a permanent negative region and positive region, so water is polar. Nonpolar, you have an even charge distribution. So if we have carbon tetrahydride or we have carbon tetrachloride, you'll see in either case the distribution of the charge is symmetrical and even, and thus there's not a disparity, and these are nonpolar molecules. Now, ionic, we also have these terms ionic and covalent. Ionic compounds are made with a metal and a nonmetal. And again, a metal is generally on the left side of the periodic table, going to that metal-nonmetal stairway, and it will be donating electrons. The nonmetal is on the right side of the periodic table, and it will be receiving electrons. So this sodium gives an electron to the chlorine and makes these ions. You have the sodium ion and the chlorine ion. The sodium ion will have a +1 charge when it loses the electrons. The chlorine ion will have a -1 charge when it gains the electron. Now, covalent compounds, instead of having electrons donated or stolen, covalent compounds, they share electrons. So in carbon tetrafluoride, you would have, fluorine has 7 valence electrons, it's a halogen. Carbon has 4 valence electrons. So for each of the 4 fluorines, carbon will share 1 of its electrons, and fluorine will share 1 of its electrons, which then means that each will have the 8 valence electrons in the full shell for each of the fluorines and for carbon. And you can draw the bond here either with the 2 dots or with the line. So this would be a covalent compounds. Now, ionic compounds tend to be metal, nonmetal. Covalent compounds are nonmetal, nonmetal, with sharing of electrons. Now, there's kind of a couple ways that things dissolve. One is solvation, where solute particles are surrounded by solvent particles. You'll often see this in when covalent substances dissolve, such as when sugar dissolves, either sucrose or glucose or anything. You'll get solvation happening. Dissociation is another type where you have the attraction between the solvent and the solute particle is strong enough to actually split the ions of the solute apart. And you see this with ionic compounds like NaCl. Now, the rate of increase of dissolving can be increased if you stir, if you increase the temperature, or something like that. And this is just a little picture. So glucose will tend to, it doesn't split up. You don't break up the glucose molecule. It will just separate from other glucose molecules because of the strength of the hydrogen bonding between the glucose and water. Whereas with NaCl, the Na actually gets pulled away from the Cl due to the strong dipole-dipole interactions between the water and the sodium and the water and the chlorine, and it dissolves that way, splitting into the charged ions. So you have the plus sodium and you have the minus of the chlorine. So if we had here, rock candy is, it's sucrose. So here you have a whole molecule. It's a covalent molecule, and it will tend to do solvation, not dissociate. It will split into individual molecules, but the molecules themselves don't split into ions. Now, solubility is the maximum amount of solute that can be dissolved in a solvent at a given pressure and temperature. And so both of those will impact the solubility. Generally, for gases, solubility often decreases as you increase temperature. For solids, it tends to increase. So we can actually look at something called the solubility curve here. And the curve shows the amount of solute that will dissolve at a given temperature. So you'll see, you basically get this line. And this line represents the maximum amount of a substance that will dissolve into a solvent at a given temperature. And so you see in this case, as you get warmer and warmer temperatures, the amount of stuff that will dissolve goes up. Okay? Now, if it exactly matches, so if this, if the little amount of stuff that's in there is on the line, the solution is known as saturated. So this line represents a saturated solution. If, on the other hand, you had less stuff in there, so if it was whatever that is, 68 degrees or something Celsius, and you only had 70 or so milligrams per milliliter of the solute in there, notice you can actually fit more solute in there that's not present. So this would be an example of an unsaturated solution where you could add more and it could continue to dissolve. So you have some of the solute in there, but not enough to make it saturated. Um, the flip side of that is there are certain situations where if you heat a substance up, dissolve a lot in it, and then cool it down, you can actually get what's known as a supersaturated solution, where you actually have more solute dissolved than will stably stay in solution. That's how you tend to get crystals formed. So on Earth, crystals are generally formed when you get really hot water coming out or into some cave or something, and then as it cools, it becomes supersaturated. And then you'll have basically the crystal will get deposited, the molecules or the atoms will get deposited onto the crystal, and crystals will grow over time in this situation. And again, so a supersaturated solution is at a given temperature, you have more solute dissolve into the solvent than can stably fit. Now, if we were to see this curve, this is a solid, and we see the general trend with solids, you tend to see an increase in solubility as temperature goes up. So to kind of recap the three situations, we have unsaturated solutions, and basically that is a situation where you can dissolve more. So if you put some solute into water and it dissolves, the solution is unsaturated. You keep putting it in and it keeps dissolving. Once you get to the point where you put it in and at this point, it's going to dissolve, but if you add any more, that stuff won't dissolve. That point right there would be a saturated solution. Okay? And then a supersaturated solution is generally formed by heating a substance up, dissolving lots in it, and then cooling it down so that there's more there than dissolved. And then if you have a little seed, what's known as a seed crystal, if you put a little tiny speck of the crystal in there, that provides something for the solute to adhere to, and all of a sudden you'll get a crystal. And you go back down to saturated, and you'll get a crystal within the container. Okay, so just to kind of show trends here, with solids, you tend to see an increase in solubility as temperature goes up. In contrast, with gases, you tend to see solubility